you've got a faucet, a pipe. This is a pipe, and water is flowing through there. So water is going to flow from high pressure to low. It's going to move in this direction, this way. And we talked about viscosity. And when you have viscosity, you get more water flowing towards the middle. The speed of the velocity in the middle is going to be much bigger than the velocity towards the edge. And at the very end right here, right next to the surface, the particles of the water aren't actually going to move up. So this is just a cross-section of what's going on here. And another thing you should remember when you see a picture like this is that this is in 2 dimensions. A pipe is in 3 dimensions. So if we're looking at something in 3D, the water is flowing fastest right through the middle, and around the surface, the inner surface, it's not going to flow at all. We want to know what the velocity is as a function of position. So as we move outwards, what would the velocity be? We already know that the velocity is going to be greatest at the center, but as you're moving outwards, what is it going to be? How would we calculate that? Well, we have this diagram here, and I'm looking at just a pipe, a part of the pipe, where there's going to be some pressure here and then some pressure over here. And the pressure here versus here, there's going to be a distance that's defined as L. And is there anything else? R represents the velocity at any of these inner rings. Okay? So each of the concentric rings inside of here are going to have the same velocity because they're the same distance apart from the center. All right. I need a different color. There it is. Whoa. So how are we going to come up with an equation for velocity as a function of position? This is going to be Poiseuille, I believe that's the French guy's name. Poiseuille's law is what we're going to be deriving. And we're going to start by talking about the pressure. We know that pressure is equal to the force divided by the area. But because there's a difference in pressure, we're going to rewrite this a different way. We're going to say that the force is going to be given by the change in the pressure, because there's 2 different pressures here. So we'll call it P, high pressure minus low pressure. So it's going to be P1 minus P2. So that's the change in the pressure from high to low, multiplied by the area. So I'm multiplying A to the other side. And the area of this sphere, any part of the circle, is going to be given by pi r squared, lowercase r squared. So that's what the force is. And it's not just any force. This is called the driving force. Okay? The driving force. So we're actually going to be referring to forces here. There's a force going in this direction here. Now, there's going to be a force from the viscosity that's slowing it down. And there's a name for it. You don't have to laugh at it, but this is actually the actual name. It's called the retarding force. And the retarding force, or the force that's slowing it down, the retarding force is going to be given by this equation right here. The coefficient of viscosity multiplied by the area that it's going through, multiplied by minus dV over dr. Okay? And the reason why this is negative is because as you move outwards, as you go from the center moving outwards, as r increases, the velocity is going to decrease. So this is the change in velocity as a function of r. But as we move from the center outwards to the inner surface wall, the velocity is decreasing. So you need to put the negative sign there. And I can bring it to the front here as well. And we will get negative mu times a dV over dr. Maybe I could derive this equation later. But that's the, I don't want to call it drag force because we're calling FD to be the driving force. So that's why I'm going to use FR instead, which is referred to as the retarding force. And so we have these 2 forces. And what we want is the velocity here to be moving at a constant speed. So this velocity at the center is moving at a constant speed. This velocity is moving at a constant speed. This velocity is moving at a constant speed. And if all the velocities are moving at a constant speed, we could say that the flow of water is in steady state. So steady state just means that the velocity is constant, and therefore the equilibrium, it's an equilibrium, or in other words, the force, the net force is going to equal 0. So the driving force minus the retarding force, which is the only two forces, has to equal 0, and therefore the driving force is equal to the retarding force. So what is the driving force? Well, we already wrote it down over there. So I'm just going to set these two equations equal to each other. We get the difference in pressure times pi r squared is equal to negative mu times a dv over dr. So we have that. What can we do here? I could separate the d and the v to two different sides here and solve for the velocity as a function of r, because that's my goal. I want to try to solve for velocity as a function of r, so I need to separate the dv and the r. Well, there's an r term here, so I got to bring this r term, and then these are constants. So I could write this as, how am I going to write this? I write it as negative dv is equal to pressure 1 minus pressure 2 pi r squared divided by mu times a. And a, I guess I could write it over here. A is the area of the inner surface wall. So the inner surface wall is given by 2 pi RL. Yeah. So area is equal to 2 pi RL. So that's the inner surface wall right there. And so I'm going to divide this mu A over to this side right here. And it's going to be mu times 2 pi RL. And I should use big L because it's the length from those two positions. And that's how I defined it. Okay, so we have that. And am I missing anything? I got to multiply this side by that dr as well. There we go. So I'm left with this equation right here. Whoa, don't fall. And then what could you do? You integrate both sides. You're going to integrate this side. You're going to integrate that side. So what we're going to end up over here is negative v. And then over here, now I'm not going to take the definite integral. I'm just going to take the indefinite integral. So I'll add a plus c to it. Because you don't actually ever see me do indefinite integrals. But I'll do it for this one. So over here, we're going to have P1 minus P2. One of the r's cancels out. So am I missing anything else? Oh, the pi's cancel out as well. So we get r in the numerator. Whoops. R in the numerator. And then you get mu times 2 times L. That comes all out of the integral. And what we're left with is r dr, if I did that correctly. So when I integrate this side, all the constants can come out, and this is the integral I'm left with. So what we have here then is negative v is equal to pressure 1 minus pressure 2 over 2 mu naught L multiplied by r squared over 2, I believe, r squared over 2. And then we're going to add to it plus c. So hopefully you can see that. The velocity as a function of r, I should write it like that, is equal to this right here so far. And then the last thing is we just need to put in a boundary condition to solve for c. And I'll do that over here. So I'll rewrite the equation. Let me just get my eraser. My eraser, where are you? Okay, so I'll rewrite this equation up here. We have negative V is equal to, that you probably can't even see that up there. And this thing is running out of ink. Let's use a different color. Come on, give me some brown here. Negative V is equal to P1 minus P2 2 mu times L R squared over 2 plus C. So that's what we have there. I'm going to erase this. And then from this equation right here, we know that the velocity at the very end is equal to 0. There is no velocity right at the surface right there. It decreases as a function of position. So we could say that the velocity when little r is equal to big R, because this is velocity as a function of position, is going to equal 0. So what we do is we just take this and put it into here. We get 0 is equal to row 1, row 2, 2 mu naught, 2 mu naught, not mu naught, 2 mu L big R squared divided by 2 plus C. And from here, we can subtract the C, or we could subtract this whole term to the other side, and we end up with C is equal to negative this term right here. So once you have the C, you can plug it back into your equation up there, and we will get negative, where can I write this? I'll write it right here. Negative V is equal to, let's see here, how am I going to do this? I'll just write it out first time. P1, P2 over 2 mu naught L R squared over 2 plus, I guess I could make this a 4. Make my life a little bit easier. Plus C, that's C term. So this I'm putting right here, and then I have to add the C to it, so plus this number right here, which is a negative P1 minus P2 R squared divided by 4 mu L, because it's 2 times that. So that's what our velocity is, and we just need to change this to a negative sign. We just need to get rid of that negative sign that's over here. You get over there. So I'll bring this to the other side, and I'll factor some stuff out, and we will get velocity as a function of R is going to equal P1 minus P2 over 4 mu L, parentheses, and then we just flip the signs here because it's negative, R squared minus little r squared. And I think that's correct. Yes. So this right here has a name. It's called Poiseuille's law. Poiseuille's law. Poiseuille's law. Some French guy. It's a very important equation, as a matter of fact, if you're doing engineering and you have to study fluids. So this is kind of a big deal equation. Okay, so we have that equation, Poiseuille's equation, and now we're going to do something with it. We're going to calculate the discharge rate, the equation for the discharge rate. And what is the discharge rate? So I got to go back to this picture here. I'm going to erase all this. And so the discharge, when we talk about discharge rate, What we're talking about is how much water or fluid is coming out of this. It's how much is being released. And so what do we mean by how much is getting released? It's the change in volume over the change in time. That's what we define as the discharge. How much is coming, how much of the water is actually coming out from this part of the pipe right here. And we have an equation already for dV dt. That was A times the velocity, right? Where we also have an equation for velocity now from Poiseuille's law. Poiseuille tells us that the velocity as a function of r, position, is equal to, I'll just write it over here because I'm not going to write it again over there, P1 minus P2 divided by 4 mu L, big R squared, minus little r squared. So we have the velocity term, but the problem is I don't want velocity as a function of r and some function of t as well. Okay, so what could I do to alleviate this? I'm going to say we're going to let this thing, which is technically considered a constant, equal, let dV dt dV over dt equal Q. So we're going to define Q as our discharge rate. If you see the letter Q, that means the discharge rate. Okay? And what we're going to do is instead of looking at the entire discharge rate, Q, we're only going to look at a little bit of the discharge rate. So what I'm going to do is I'm going to draw just a little bit of it in this ring right here. And in this ring, this little tiny ring has a thickness. It has a tiny little thickness, which we can define as d little r. So dq, which is the amount of fluid in that ring, which is that little bit, not the entire fluid that's coming out, but just a little bit of the fluid, can be given by the equation V dA. And where am I getting this V dA? Well, this term is equal to A times V. So if I take the derivative of this, I have to take the derivative of that. So taking the derivative of this, which means this, that's dq, I would have to take the derivative of that term, and I get V dA. And we could rewrite that one more time as V times, because we want it in terms of R. So dA is really just 2 pi r dr. I'm hoping you've actually seen this before. This is identical to when we were talking about charges on a disk. So charges on a disk, we would write dq and then sigma times something, sigma times dA. So this is almost close to it, except we're not talking about some charge. We're talking about speed here times dA. But it's almost similar, the idea. So dq, we're going to write as the velocity times this term right here. Okay? And we know what the velocity is as a function of r. So I could replace v with this term right here, and then I can solve for the total charge dq. So I'm going to integrate this side, and I'm going to integrate this side. Where? I'll do that on the next page. Hold on, my notes are about to fall. Don't fall. Whoa, oh no. Oh no. Patrick fell. Mayday, mayday, mayday. I'll figure this one out. Oh man. How did she put it together now? Now I'm curious. All right, I'll worry about that later. Ugh. Let's fix this first. How dare you both laugh at real life problems? If you had a loved one that was decapitated, I'm sure you wouldn't You wouldn't be lolling. Okay, so I'm going to rewrite the equation. I have dq is equal to the velocity, that velocity term. So v first, I'm going to put that in. That was rho, not rho, why do I keep saying rho? P1 minus P2 over 4 mu L r squared minus little r squared. So that's the volume. And then we got to multiply it by 2 pi r dr. So that's our equation for the entire discharge. If I want the entire discharge, I have to take this term from 0 to big Q. I would have to take this side from 0 to big R, and that would give me the entire discharge. So how much water is actually being released? All right, so this just becomes Q. And over here, what could we do? We could factor out some stuff. We could take all this out, the 2 pi's out. And so the pi and this thing would cancel. So I have P1 minus P2 pi. And then the 2 and the 4 become a 2 mu L. Okay, so that's been taken out of the integral. And I'm left with an r and this term right here, which I will distribute as r squared times little r minus little r cubed dr. So I just distributed this r into here and here. And I took everything else out. And we're evaluating this from 0 to big R. So we get that Q is equal to pressure 2 times pi over 2 mu L. And this term becomes R squared times little r squared divided by 2 minus little r to the 4th divided by 4, evaluated from 0 to big R. I believe I did that correctly. And then we get Q is equal to P1 minus P2 times pi divided by 2 mu L. And this thing will become r to the 4th over 4. Am I saying that right here? This would become, oh no, r to the 4th over 2. And this is r to the 4th. So I'll just write it out. Big R to the 4th over 2 minus big R to the 4th over 4. And this term, when you clean it up, is going to equal big R to the 4th over 4. Okay, so when you subtract those two values, that's the value you end up with. And then the last thing we need to do is just clean this up and write down our equation. So Q is going to equal P1, P2, so the higher pressure minus the lower pressure. Sometimes in textbooks they write it the opposite way. Just know that P2 represents the higher pressure. So we get pi big R to the 4th. And in the denominator, we have 4 times 2, which is 8, times the coefficient of drag, times the length of the pipe. And this is your equation of discharge. Dang, I am just not having a good day. So there it is. I think that's all I wanted to talk about for today. Yeah, that seems about fair, good enough to end a Friday with. So this is the discharge equation for a fluid that has viscosity in there.